Okay, so yeah, that looks good. Okay, all right, off we go. So let's see, last time, we finished with this example last time, and I just want to say one other sort of super quick thing about it. You may recall that I started the discussion of this example with the observation that we've already established that for this scenario, x is locally a function of the other variables. We did so in this previous example, is x locally a function of the other variables, right? So the observation I want to make here, this is super quick, but because we already did the details, but you cannot assume generically most of the time. It's just not given. You cannot assume that it is given that the whatever the variable is that they've asked you to take a partial derivative of actually is a function. So in some sense, neither one of these examples here is really a complete example, right? So this example here assumes, I mean, this is a rare thing in the statement of a question for me to tell you, in advance that x is locally a function of y and z. That's sort of standing on what was previously built in this example, right? So typically, how this will go down on a test, for example, or if there's a homework exercise, typically what you should expect to see is basically this, where this is not given. And when you see this, so, we have a surface described by an equation. We're interested in what's going on near a certain point. Compute partial of x with respect to z. It's your responsibility. It's on you, right? This is part of the deal, part of the job, is that you have to recognize, I'm being asked to take a partial derivative of something that I don't even know to be a function. So, oh my gosh, I'd better step one, I'd better ask and answer, establish that indeed it is a function of the other variables, and then proceed to computing its partial by way of this method. So that's what you should expect on any question, unless, in again, the rare circumstance that it happens to be given. That's weird and unlikely and unnatural, right? So make sure you include both parts. So this is an important part of the solution, to check that the thing you've been asked to take a partial of is something you're allowed to take a partial of in the first place. Okay, and for whatever it's worth, it's typically about half the points, right? On a question like this, about half of the points would go to establishing that the thing that's supposed to be a function actually is, and about half the points would go to computing the partial derivative it asked about. FYI. Okay, so moving along, Chapter 3, starting with 3.2, because we've already done 3.1. Remember, I like to do 3.1 early because it gives me a point of view on derivatives that is very helpful for doing the chain rule the way I want to do the chain rule. So, okay, with 3.2, we're going to go quickly through this section. This material doesn't, the first part does. A lot of what happens in 3.2 doesn't really connect up to later things. So anyway, here it comes. This first part is important. We're going to be looking at a parametric curve. Position as a function of, again, usually time, right? And I just want to establish certain notations and relationships between them. And here we go. So if you have a parametric curve, you can talk about the velocity, right? Velocity times time gives you displacement, right? So this velocity vector that I won't put on the diagram, velocity times time gives you displacement, and that displacement we're going to refer to as dx. And I think this is actually a really natural notation I like very much. We call that dx because d says differential, x says position. A differential is a linear estimate of a change in whatever thing. So dx, the immediate interpretation of dx is that it says, what is our linear estimate of how much position changes? And that's exactly the job that it's doing in this little story here. Right? Okay. Now there's a related quantity, which is, I'm going to call ds. Pretty standard notation to use s to represent arc length. So ds would say, okay, how long is a little bitty piece of the curve? And so I'm going to represent that on the figure like so. And it's a little bit of a bogus indication because it is, in fact, very importantly, ds is the linear estimate of the length of that little piece of curve. It's not the actual length. But if I put it right on the dx arrows, sort of, the shaft of that arrow, it becomes hard to see. It's basically the problem. So anyway, the big idea is, how long is that little piece of curve? Well, we have a vector dx that's telling us the displacement, and shouldn't the distance be the magnitude of the displacement? Right, so this is a pretty natural thing to write down, and using the formulas above, alternatively, you can write it like that, or this down here you can also interpret as just distance equals speed times time. Right, pretty natural. Okay, couple other observations we need to make. There is a vector that I'm going to call capital T. It's the unit vector pointing in the direction that you're going. It's very handy in various circumstances when you're doing stuff with parametric curves to be able to talk about the direction alone, right? And of course we represent directions with unit vectors typically. So the unit vector going in that direction is a natural thing to talk about. We're going to use capital T for that purpose. The book does as well, and it's a very common choice. Okay, not hard to see, of course, how to compute that vector. It's a unit vector pointing in the direction of the velocity. That's how we compute unit vectors. Okay, how are we doing so far? Okay. All right, with all of that set up, and by the way, all of the references that I've just made to what's going on in that curve, all of these objects and notations and relationships are going to figure very prominently when we get to chapters 6 and 7. So this is not just for section 3.2 purposes. All of this is going to figure very prominently later on. Okay. All right, let me clean up my mess. And let's see here. The last thing I want to talk about is this product right here, TDS, and I claim that TDS is the dx vector. And there's a couple different ways that you can see this. One way to do it would be, let's see here, would be to interpret T by that formula, and ds by this formula. And let's see here. Let's see. We have a magnitude of v in the denominator and in the numerator. That cancels, and we get just v dt, which is that, which we've already established is the dx vector. That makes sense to everybody? Okay. Now here's a different way to see it, and I'm all about seeing things from multiple points of view. It's a really important idea in math. Don't just have one point of view on things. Try to have as many as you can. Another way to think about this product is, well, I see a unit vector and I see a scalar, and that means that what this is a direction and magnitude breakdown of whatever this product is representing. All right? We represent directions with unit vectors. Whatever scalar you multiply by then will tell you the resulting magnitude. All right, well, the magnitude of this vector is ds, just like dx is. The direction that this points, well, this points in the direction of the motion, just like dx does. I think this is actually a really nice point of view. This product, TDS, immediately agrees with dx in magnitude, it agrees with dx in direction, and if it looks like a duck and quacks like a duck, it's a duck. That's the basic idea here, right? Because direction and magnitude define vectors. So you don't even really need to use any algebra to see that these are equal. It's you can just kind of think about the qualitative features. All right. Okay, so we are now armed to write down a formula for how to compute the total length of a parametric curve. It's just a matter of adding up a bunch of little pieces of length. And again, we've already discussed, we have this formula, we have this object defined called ds. That represents the length of each little piece. You just add up over the entire curve. In other words, add up for all of the, as you break it up, add up over the entire range of values of t, in other words, and that gives you this formula right here. Recalling, of course, let me clean up my mess again, that ds is v dt, magnitude of v times dt. Okay, everybody all right? Okay. All right, easy example. This is very plug and chug here, so I'll be super quick about it. Here's a parametric curve. Notice if I have position, I can compute velocity without too much trouble. Taking the derivative of that gives that for the velocity. Notice now here I am looking literally at, switching colors, I'm looking at the magnitude of the velocity, as I should be, and doing an integral over all the values of t, right? So t goes from 0 to 1. This integral will compute the arc length of that little parametric curve. And you multiply it out and collect terms, and you get a nasty integral, and I don't want to do it. And y'all don't want to do it either. And sadly, I'm sorry to report, very often when you write down these integrals, you're going to get pretty undesirable integrals. Because you can see right here, the integrand is a magnitude. Magnitudes are computed with square roots, and square roots make integrals hard. That's just how the cookie crumbles here, right? So, they tend to be hard to compute. Too bad. Okay, so this allows us to define a new concept. This new concept is useful in a lot of abstract ways that we're not really going to do much with in this class. But this does need to get said. It turns out there are, as you all know, lots of parameterizations of any curve. The parameter could just be any way of indicating some sort of a distinction of what input value gives you each point on the curve. So for example, if I look at this parameterization right there, it's pretty easy to see that it satisfies that equation. So this is a parameterization of that curve. Well, here's the thing. This weirdo formula right here also satisfies that equation. So this is also a parameterization of that same curve. And there's, of course, many, many, many more. Right? So the point of view I want to take on this is that I have done what we call reparameterize this curve by plugging in for one of the parameters. You can see I've taken every t there and replaced it with this expression q cubed plus q. Right? So anytime you do such a thing, you're literally just changing what the parameter is that you're using to describe how you want to trace out the curve, right? So a couple of little asterisks. This relationship has to be monotonic and bijective, and I don't want to get into the weeds. But anyway, in very many cases, you can reparameterize, and all you really need is a relationship between the parameter you have and your new parameter that you want to use. Okay, so turns out we have already a natural choice for a new parameter. It's arc length. So what I mean by that is, given a point here, on the curve. And this, by the way, assumes that we have a fixed reference point that I'm going to call the starting point. That's going to be where t is 0, whatever. So at some point that I have highlighted in purple there, I could describe this by what is the value of t that would give you that point in whatever my existing parameterization is, or I can describe that point by what is the arc length that it took me to get to that point. And I know that seems weird, right? This idea of using distance as a parameter to describe location on a curve, but I claim you all have actually seen this in your everyday lives probably. You may or may not have noticed. But when you're driving down the freeway, they have what they call mile markers. Mile markers are arc length parameterizations. They literally give you position by where did they stick that sign into the ground, right? That's position on the curve. And the parameter that tells you where that goes is, well, how many miles are you from the reference point, which is usually like the state line or the county courthouse, or so they have whatever rules they want to use depending on the location. So it's actually a pretty natural thing, right? And so if we're going to say that we're going to use a t parameterization to create an s parameterization, we just need a relationship between them, and then we have it. The relationship between an original parameter t and arc length s is compute the arc length. It depends on, of course, t. So no big deal. The integrals are weird, but in the abstract, it's no big deal to write that down. Now, why do we like arc length parameterizations? I'm going to make a pitch on this first one here. It is intrinsic to the curve, because this point, for example, saying that that point is described by, well, it's that many miles away from the state line, literally intrinsic to the curve. It doesn't depend on the driver. Right? The mile markers, like there's a mile marker on my way home, right? That's like, what is it, like 160 or something like that, I forget. Mile marker 160 is always in the same place. If I'm driving fast, if I'm driving slow, whatever, the mile marker doesn't care about me. The mile marker is intrinsic. It stays put because it only depends on the road itself. Therefore intrinsic to the curve. If I were to say, hey, let's parameterize a curve by follow me as I drive along that road, position is a function of time, that's not intrinsic to the road. That depends on me. If I drive fast, we get one parameterization. If I drive slow, we get a different parameterization. Not intrinsic to the curve. So there is something powerfully natural about the idea of a parameterization that is intrinsic to the curve, and this does that. It's pretty cool. Yes?
For x prime, what variable are you using? Is that
yeah, that's the thing. This is annoying, right? But if you want to know the amount of arc length that it takes to get to the point where you would have been at time t, the problem is that now t is the upper bound for your integral, and so now you've got to consider all the values between 0 and t. What am I going to call these values between 0 and t? I can't call them t, right? And so this is the lowercase Greek letter tau, which we use because it's vaguely reminiscent of a T, right? And it just indicates that it's playing the role of keeping track of all the different values of time as I drive along the road. I just can't call it T. So it's just a different dummy variable. Is that cool? Yeah. Right. Okay. All right. So let's do one. Other cool properties. Arc length parameterizations have unit speed. That's pretty neat. Here's a quick example. Here's a parameterization. Let's try to make an arc length parameterization. Well, I need to compute the relationship between s and t. So I need to compute this integral. Got to compute the velocity. right? The velocity comes out of taking the appropriate derivatives. You got to compute the magnitude of that velocity. Magnitude, of course, is the square root of the sum of the squares of the coordinates. And then you got to do the integral, and this is where life gets uncomfortable. And you got to crank it out. It's an ugly integral. And I went to some trouble in this case, by the way, to generate an example where what we had under the radical happens to turn out, in this very carefully constructed example, happens to turn out to be a perfect square. And that does not happen automatically. It won't happen most of the time, right? You'll mostly end up with a nasty integral. But again, I conveniently arranged for this one to work out nicely. That makes for an easy integral, and that makes for an easy relationship between S and T. Here's the problem. If I want to use this to reparameterize, I would need to solve for T to stick into the original parameterization. And despite all that trouble that I went to make this integral work out, it still remains that I can't solve for T, right? So, yeah, it's annoying, right? And in practice, day in and day out, yeah, most of the time it's impractical in most circumstances. Yes?
What is the, squiggly T?
That's the lowercase Greek letter tau. I was just telling him it's a placeholder. I can't use T because T is a bound, right? So it's just it's what we call a dummy variable. It's just a different placeholder to represent all those values.
I'm sure it was significant.
Yeah. It's it's a necessary weirdness. Yeah. Okay. So anyway, there it is. Let's move along. Section 3.3, we're going to talk about vector fields. This is a big deal in chapters 6 and 7. There are pedagogically different ways to introduce vector fields. Some books introduce vector fields when they're needed, which would be later. Some books, like ours, introduce vector fields early, which has the advantage of letting y'all have a little time to kind of digest and get used to this new kind of mathematical object that you hadn't probably seen before. We can't assume you've seen before. Anyway, we're going to introduce them early. The downside of this early introduction is that we're going to introduce all this stuff, and then there's not going to be any immediate sort of what did we study that for? Right? So the payoff for this is going to come later. So you're going to have to be patient and wait for that. That's just, again, the choice the author made. Okay, so here we go. What is a vector field? Most fundamentally, a vector field on Rn is a function from Rn to Rn. That's sort of most fundamentally. Now, importantly, we interpret the input as being a point, like so, and then the output, we're not going to interpret the output as being a point in another copy of Rn. We're not going to draw the graph. We're not going to try to emulate something like a parameterization or anything like that. When you're talking about a vector field, you view the output as being a vector in that same Rn that your input point came from. So this is how we view a vector field. A vector field consists of a bunch of points with arrows coming out of them. And you can see such in various different places throughout the Rn. Typically we draw a representative collection of such points that are the inputs and arrows representing vectors, which are the outputs. Is that cool? We add that now to our collection of different ways that we view multivariable functions. Right? It's not a graph, it's not a level set. This is not. We haven't parameterized anything here. This is not a literal domain and target, type interpretation. So this is now our fifth different point of view on certain kinds of multivariable functions. Yes?
A vector field is necessarily bijective.
No, I hear where you're coming from. Yeah, they don't have to be. So I'll show you an easy counterexample. Here is a vector field where you're going to notice it's always the same output, right? Always just a single constant, and that's totally fine. The fact that you have the same output just means that the arrow, no matter where you're looking, the arrow is always that representing that same vector, and that is for every input point. Does that make sense? Yeah. Right. Okay, is everybody okay with that first example? Okay. All right, let's see next example. This next example is a little bit weird. This takes a little bit of kind of thinking through. You look at the formula here, that f of x comma y is x comma y, and it kind of feels like, well, shouldn't this be like, I don't know, like a straight line or something? Right? It's this simple little formula. It feels like it ought to be a simple resulting picture. Cannot emphasize enough. We're not drawing a graph. So don't ask yourself what something like this ought to look like were it a graph, because this isn't. Right? So what we have to think through is, again, just following the procedures. Following the procedures for any input point. So we'll consider at some point x comma y. What is the corresponding vector? Well, the corresponding vector. There's the formula for my corresponding vector. You'll notice it's really the same as the input point. The problem is I have to interpret the output as being a vector. Right? Now, so how do I interpret what I might have originally interpreted as a point? How do I reinterpret that as a vector? Well, again, flashbacks to linear algebra, but you talk about the position vector for the point. Right? In fact, let me do this in purple, because it really is just a different way of viewing the input. Right? That input point, were I to view it as a vector, it would be that position vector. So that is what I'm going to copy. That is what I'm going to say is what xy is. Xy is the vector represented by that arrow. But then I have to remember, oh wait, that's not how you draw it. The way you draw it is the output is drawn with an arrow that has its tail at the given input point. So I've got to take this green output vector and draw it where it's supposed to be, namely with its tail at the input point. Is that cool? Now, if you repeat this process, now geometrically what you're going to notice is that this vector field, what it looks like is wherever you are, this field vector is always just further in that direction, right, by the same magnitude. So not hard to persuade yourself that you're going to get a bunch of arrows that they always point radially outward away from the origin. The farther you are away, the longer they are, as I have drawn here. Everybody happy? Yeah. Okay. All right. Okay, here's another weird one. By the way, I'm showing you a bunch of examples of these because, again, this is a different way to construct a picture, right? And so there's a completely different intuition for looking at a formula for a vector field and trying to figure out what does that thing look like. So I'll show you a couple of examples just to get the ball rolling on that. And the more vector fields you see, the more you'll get the hang of how this process works, and it'll become intuitive eventually. Okay, so let's think about this one here. We have input points, x comma y. So here's a point, x comma y. And then you look at the field vector, negative y comma x. And, different ways to interpret this. But y'all may notice, just algebraically, that this is what you get when you take x comma y and do a quarter turn counterclockwise. Now, I'm going to remind y'all real quick. I know linear algebra may have been some time ago, right? Linear algebra is a prereq for this course. I am going to assume that you're good to go on what I'm going to call the basics of linear algebra. We're not going to do any Jordan canonical form in this class. There's not going to be any Hermitian inner products in this class. Nothing like that, right? But I'm going to assume you're strong with linear transformations and geometric examples of linear transformations like rotations and shearing transformations and magnifications and stuff like that. If you might be a little finicky, if you're concerned here that you don't really remember how that works, come talk to me in office hours. Let's get that straightened out, right? Happy to help. But that is something that we do need to get straightened out. Okay. All right, so I claim this is a quarter turn counterclockwise. But that would, again, assume that I interpret the input as a vector. So I have to interpret the input as a vector. There it is, the position vector for that x comma y. The quarter turn counterclockwise would give me something like that. And then I have to remember, but we draw the output field vector with its tail at the point that was the input. And so that's why, for that purple point, this green arrow that I have highlighted, it represents the field vector at that point. And y'all can do more examples of the same, and y'all will produce this picture one point and arrow at a time. Is that cool? Okay. All right. Okay, so what does this look like? What is this? What physical scenario does this sort of suggest? You might say by the picture. And I tell you what I see when I see this. I see somebody has a pot on the stove and they stirred the pot counterclockwise, and I see a fluid that's kind of going around like so. You know what I mean? So for whatever it's worth, that is one of the primary interpretations that we have of vector fields. Why, in other words, is it that we would ever want to do such a thing? I mean, what's the point to this weirdo construction and this weirdo picture that we decided for seemingly no particular reason? Why do we do this? Well, among other reasons, so that we can describe fluids flowing in some context. Pretty good example. Okay, here's another example. This vector field right here, which I'm going to rewrite just for convenience. I'm going to rewrite like that. And written in the second form, easy observation that wherever we might happen to be, whichever x point we are looking at, notice that is just the unit vector pointing in the direction that x vector is. So that's just defining, That's just defining this direction, right? And that's what we're going to call a radial direction, because it comes out of the origin radially, right? And then look at the magnitude, the resulting magnitude. You can see right there that magnitude is inverse square. Right? So the farther we are out, the greater the magnitude of x, the smaller, in an inverse square way, the smaller the magnitude of the field vector is. So that's why we get longer arrows close to the origin and shorter arrows farther from the origin. Is everybody on board? Okay. All right. All right, and so now why is it pointing inward instead of outward? I chose this C to be negative to track with this interpretation. This, with a negative value of C, this is what gravitational fields look like. Right, so given a location, given an X, with a large amount of mass at the origin, creating a gravitational field, this formula here tells me the gravitational force. How we doing? Okay. By the way, electric fields look exactly the same, with a different constant, obviously. It depends on the charge instead of the mass, and there's a bunch of physical constants that are somebody else's problem, right? That we don't have to worry about because we're doing math, right? All of the units and invariance of the universe, stuff like that. Yeah, constant. We'll just lump that in, call it C, right? And with that in mind, electric fields and gravitational fields look exactly the same. Okay. All right. Okay, so notice I've got a nice opportunity here to point out we have two different pictures of two different vector fields about which we have now made two highly contrasting interpretations. Right, this first picture up here I'm interpreting as a fluid flow. There's nothing about forces there. There's no gravity there, right? That's a flow of a fluid. Here's another example of electric field. Of a vector field, and no fluids, at least not that we've discussed here, right? This is a totally different physical scenario where we're talking about forces, not fluids. So this is nice. It's good to have different physical interpretations, manifestations of mathematical objects, because it gives you different ways to think about them. And it also gives you different physical scenarios to which you can apply them. So what we see here is that vector fields are going to be a useful tool in understanding fluid flows. Vector fields will also be a very useful tool for understanding forces, such as gravitational forces, electric forces, etc., magnetic forces. Okay, so it's important to be able to understand, to develop intuition for vector fields in both of these senses. Okay, another example. Oh, why don't I do that? That's better. Here is a old idea. Y'all remember gradients, right? If you have a real valued function, you can talk about its gradient vector. And we know that gradient vectors always point uphill on the graph, right? That's all old news. What's not old is this observation that this thing called the gradient gives, for any given point where you might want to evaluate it, a corresponding arrow representing the vector that is the gradient vector. Oh yeah, that's a vector field. This is an innocent observation. For every point, you can compute the gradient. Therefore, at every point, you have a vector. That is exactly what a vector field is. So that combined with our old interpretation that gradients always point uphill on the graph allows us to look at this example right here. You see we have a real valued function. Here is the graph of that real valued function. Here's the gradient formula. The gradient vector field, which you can see is sort of radial outward, like so. And check it out, as it should be, it points uphill everywhere in the domain. So, just innocent observation. One last observation I'll make about gradients, and this is foreshadowing, and we're nowhere near armed at this point to be able to flesh this out, but I claim, and so just for foreshadowing purposes, not only are gradients vector fields, they are special vector fields in powerful ways that we will study very carefully when we get into chapters 6 and 7. So these are important vector fields. Like I say, just planting a seed. We'll flesh that out later. Okay, what are we going to call the what are we going to call how are we going to do terminology here? And so here is a scenario where I have some function, some real valued function, and then I compute the gradient of it, and the result is some vector field. So what are we going to call the vector field that results from computing the gradient? I propose the gradient, right? Why not? Seems like a natural choice. That's where it came from. We'll call it the gradient. What are we going to call the original function? In other words, if somebody comes to you with a vector field and says, hey, this vector field is a gradient of some function, what is that some function? What terminology should we use? And I propose antigradient. And I remind you, I'm just stealing a grammatical construction from derivative and antiderivative. Right? If you have a function, you take the derivative, the resulting output, you call it the derivative. If you want to go the other way, you want to undo the differentiation, you call that the antiderivative, right? I think this is very common, a very natural terminology. Here's just a heads up, cultural point, as much as I wish it weren't the case. For whatever, anyway, I know the reason, but it is actually more common in practice for this to be called the potential function, which does not leap off the page as a natural choice, right? They call it the potential function. Now, why do they call it the potential function? Well, okay, here is a common physical scenario, such as, let's consider gravity, right? There is this idea of gravitational potential energy, and there is the idea of gravitational force, and the force and the potential energy are related. If you haven't had a physics class, if you haven't seen this before, don't worry about it. It's okay. This is just an example. But what the example is, is that the negative of the potential energy is the function whose gradient gives you the gravitational force. And very awkwardly, there is a minus sign there. Roughly speaking, forces pull downward. Potential energy increases upward. That's just the way gravity works. I wish it weren't. Anyway, but that little minus sign is annoying though it is. It's very, very real. That's the way this world is that we live in. So now let's, with that in mind, you might be able to already see the problem with, what's the problem with referring to what I would call the antigradient as the potential function? Well, it kind of ignores the fact that there's a minus sign there, and it's confusing, and as completely unnecessary confusion. We don't have to call this the potential function. We could, to remove this confusion, we could just call this the antigradient, and then potential energy is the negative of the antigradient, and there's no which do you mean the potential? Which kind of potential are you talking about? Did you have the minus sign included in there or not? No problem. So anyway, I think it's unfortunate, but this is very common. You're going to see what I would like to call antigradient, very often referred to as potential function for this. I'll say with this example in mind, and anyway, super annoying. And I'm going to say antigradient. I think it makes more sense. Outside of Math219, you're going to hear potential function. Okay. Now, again, we've already discussed vector fields can represent fluid flows. Various examples of fluid flows. We tend to think of fluids as being three-dimensional things, and therefore their flows are three-dimensional flows, right? Such as how air is moving around in a room, such as this one. There's air moving around. I can hear the AC working, right? So there's air moving around in here, and wherever you might happen to look, you can talk about exactly what is the velocity of the air at that point. So very natural. Likewise for various other examples, as you see here. But I'll point out that you can also talk about two-dimensional fluids. Kinda. Surface water, of course, is an obvious sort of example. Right? But I kind of like this one, animal migrations. You can view that as a flow of a fluid. If you have a million wildebeests, and they're walking across the plane or whatever, that's kind of a flow of a fluid in a way. And a lot of people would counter, hey, whoa, no, come on. That's not a fluid. They're animals, for crying out loud, right? They're discrete things. Yeah, so is water. Water is made up of molecules. Those are discrete things. I'm just saying, right? So it's a weird kind of a fluid, but as seen from sufficiently far away, it would kind of look like a flow of a fluid in a way. All right. So here is a very important computation, really important computation to understanding vector fields as representing fluid flows. We're going to ask what I consider to be a very natural question. So suppose that you have a vector field. Suppose that represents the velocity of the fluid. So the vector field points in the direction the fluid is flowing, and the magnitude of the vector field represents how fast the fluid is flowing in that direction. And with a fluid flow, I guess I can leave that. If you were to have a piece of area, small flat piece of area, let's say, and just for algebraic purposes, I'm going to talk about this normal vector in. You'll notice I'm making a unit vector. So given this flow of a fluid and given this piece of area, I can ask a pretty reasonable question, which is what's the flow rate? How much volume per unit time of fluid is flowing through there, right? Not to be confused with the velocity. Velocity is distance per unit time for a single particle of fluid. Here we're talking about total quantity of fluid per unit time through a surface. Very different rate. Okay, so how do we compute this? It's actually not that big a deal. It's just a matter of kind of looking at the picture and putting the pieces together. So let me walk you through the calculation. In a given amount of time, a certain amount of fluid, a certain vector will represent how the what the fluid has done in that amount of time. So let's in this case I've got some vector there. So in our delta t amount of time, that's how much the fluid has flowed, and therefore we've generated a certain volume of fluid. The volume I can compute as being area times the height. Let's see what color I'll use. Red for the height here. Right, height times the area of the base gives you volume. Old high school geometry fact. Clever observation. That height, notice, is the normal component of that d vector. That displacement vector, you just got to look at the pieces here, right? But that displacement vector, looking at its component in the normal direction, is literally, that's what that height is. No? Okay. How do we compute components? We compute components with dot product with the unit vector. Thankfully, n is a unit vector, so component's just a dot product. And, so what is this d vector? Well, this d vector, keeping in mind that we have the velocity, the vector field is the velocity, and displacement is velocity times time. So this d right here, velocity times time, it means turns into vector field times time. Is everybody with me so far? All right, now I've got a huge mess on the screen. The very useful color coding for keeping track of what's going on in the algebra and how that relates to the picture, but I am going to delete all of this now so that I can wave my hands more conveniently to a certain point, we were asked here to compute the flow rate, volume per unit time. Well, there's the volume. There's the time. And that means that this F dot N times area is the volume per unit time, namely that is the flow rate. Is that cool? Okay, so nice little calculation, and let's see here. For whatever it's worth, this expression here is extremely useful for actually a couple of really good several reasons, only a couple of which are we going to see right here. But so the immediate use we have for this is that, if your vector field represents velocity, then this expression here tells you flow rate. That's a really nice interpretation. So this expression deserves a name. The name we use is flux, which is a scary sounding word, but all it is this expression right here, F dot N times the area, and the interpretation that we've seen so far is that it represents flow rate. It also deserves a notation. We're going to use capital phi for flux, right? So natural choice. And there you go. Okay, now the second use for flux that we're going to see right now, but I'm going to leave the details for y'all. This is a wonderful little exercise. I strongly encourage you to use this as a practice problem. As always, in such cases, if you get stuck, ask a friend, whatever, look it up, find your resources, whatever. But if you can't figure it out, you are extremely welcome. Come to my office hours. I'll be very happy to walk you through this. Right? Anyway, what I think it's useful for y'all to try this as a practice problem first, and that is, if you were to represent the vector field differently, if you were to use density times velocity to describe the fluid flow. Seems like a weird thing to want to do, right? If you have a fluid, the velocity is obvious. Why would we stick a density in there? Seems strange. But if you do this, in this case, then you get a different interpretation for flux. Flux, in this case, different interpretation of the vector field. We expect a different interpretation of the flux. And what you get is, I circled it wrong. You get mass per unit time. Let me do that one more time. You get mass per unit time instead of volume per unit time. So ultimately, that's the reason why. The reason counterintuitive though it may seem, the reason it actually makes sense to talk about density times velocity is because flux means something different that's natural. Still natural. Different kind of natural. So this reasonable interpretation. Heads up, going into the future, different situations, sometimes what you want is dm dt. In such a case, make sure your vector field has that factor of density in it. On the other hand, sometimes what you're interested in is volume per unit time. And in those cases, make sure that your vector field does not have the factor of density in there. Okay. All right. So, again, give this a try. A real quick hand wave as to how you're going to do this. The way that you're going to draw this conclusion that this represents mass per unit time is you're going to draw a picture that's morally equivalent to this, except instead of computing delta V, you're going to compute delta M. And you're going to write down a formula that looks a lot like this, and you're going to develop it in a way that's very similar to how we developed this. You're really just going to take this calculation I've got right here, and you're going to kind of insert a factor, a delta, in various appropriate places. Right? So you're going to shamelessly copy off of this work that we've already talked through just to adapt it to this slightly different circumstance. And anyway, like I say, if you have trouble, come talk to me in office hours. Happy to help. Okay, this next page is a super fun page, which tragically is not essential, and I don't think we have time for it this term, which is unfortunate. But this has been increasingly commonly the case. This course is just too packed. But I do want to at least wave my hands at what this page addresses. Just so you know, here's a different kind of a fluid, and that is light. You have a light bulb right there. Well, it generates photons that flow outward like so. And that's a fluid, isn't it? Kinda. It's not wet, right? But it's a very large number of teeny tiny little things, just like water is a very large number of teeny tiny little things, molecules. Right? So you can interpret this as a fluid flow. Very natural. And you can write down a vector field that represents this fluid flow. By the way, just for your curiosity, it's inverse square radial, as it turns out. So that's a weird thought. By the way, I'm going to go ahead and plant this thought while we're here. Not only are gravitational fields structurally just like electric fields, gravitational fields are also structurally just like the flow of light out of a light bulb. And that's actually going to be a really important connection when we get into Chapter 7. We're going to do some physics of gravitational fields. And this fact that gravitational fields, they behave just like light coming out of a light bulb, it's going to be a very useful perspective. Anyway, that's foreshadowing. Okay, so here is where things get weird, though. What if you have a second light bulb, and that's also shooting out photons in various different directions? And now let's ask the question, okay, at this point, right there, at that point, what's the velocity of the fluid? And this is very awkward, because on the one hand, at that point, there are photons that come from our purple light bulb, and at the same point, at the same time, there are photons that come from the orange light bulb. So which one of these is the velocity? Neither represents the velocity of the fluid. The fluid is kind of crossing over. This is a weird fluid where the particles can kind of cross each other's paths, right? Water doesn't behave that way. Water, all the particles of water kind of flow along with each other. You know what I mean? So this is a very strange fluid. How can we represent with a vector field all of what's going on here? And the big idea is to use this formula from the previous page. We're just going to kind of use this formula backwards. What we previously did is, assuming we know the vector field that represents the fluid flow, then given an area and a normal vector, you can use this formula to compute the flow rate. That's what we did on the previous page. I'm just going to turn this around now. I'm just going to turn this around and say, look, if you give me an area and a normal vector, I can empirically measure the flow rate. I can just look and see, okay, all right, well, here's my area oriented as indicated, and just look and see what's the rate of the flow rate of photons, in this case, going through that area. And therefore, I can say that the vector field that represents the fluid is just whatever I would have to put in that place to make this equation work. And it turns out that this can always be done, certain natural assumptions being made. So anyway, this can be done. There are fluids that are weird like this, and here is how we understand them with respect to vector fields. Okay. All right. We're not going to do this example. You're not responsible for it. You don't have to look at it. On the other hand, it is pretty cool. If you want to look at it, I think there's good to be gotten out of this. But again, you don't have to. In fact, just to emphasize, I'll go ahead and cross that out. Okay. All right. Okay, moving along. Let's see how we do on time, by the way. Okay, fine. Okay, so here's a nice little observation about fluids being represented by a vector field. Assuming that your vector field... Here, let me use blue instead of red. Looks more like a fluid. There we go. If you have a vector field that represents fluid flow by way of its velocity. So imagine like you've got a fish tank full of water, right? That says how somebody stirred up the tank, some prankster, stirred up the tank, and the fish is annoyed. Okay, well if there were a little piece of fish food that were in the tank, the water is flowing around, well then that little particle of fish food is gonna go where the water pushes it, right? Okay. All right, so here's the way we would say that. The particle, its velocity, right? The velocity of the particle is going to equal to the velocity of the fluid. Isn't it? That's why, that little piece of fish food doesn't have a little outboard motor on it, right? That little piece if the water's going that way, that little piece of fish food is going to go right along with the water. So the velocity of the particle is the same as the velocity of the fluid, but specifically the velocity of the fluid at the point where the particle is at any given moment. Does that make sense? So I think what we have, this equation that I've got written down here is really just a direct mathematical translation of the, I think, physically pretty satisfying assertion that the particle goes where the water tells it to go. Okay. And then we make the observation that, as indicated there, velocity of the water is what the vector field is. And so all together then, what we have is what we call a system of differential equations. Y'all have probably seen single differential equations in Calc 2 class, something like that, right? So this is a system of differential equations because we have a vector of coordinates. We're taking the derivative of both of them, and both of those derivatives have to equal to the field vector that you get at the given point, right? So this is actually a system of differential equations, and these can be solved. And how to solve those kinds of differential equations is one of the things that y'all will see in Math 353. But it's not part of this course, so I'm not going to show you how to solve those equations. I am going to show you, though, what it looks like when you get a solution, because you can take this vector field right here. That vector field then gives you one of these differential equations, and then you can solve it. And I claim that this actually is a solution to that system of differential equations. And the way you're going to confirm, it's actually really easy to confirm that this solution works, is you're going to take this formula for x, and you're going to take the derivative, just like the left side of the equation tells you to. And then you're also going to plug that formula for this alleged would-be solution. You're going to plug that into your vector field, like the right side of the equation suggests, and then you're going to confirm that you get the same thing both ways. So it's very plug and chug to confirm that you have a solution, even if it's substantially harder to actually solve in the first place. Yep?
If the particle had its own velocity distinct from the fluid, you would be able to use this, right?
Correct. Yeah, that's right. So like if the if instead of a little flake of fish food, like if you had a BB, right, and a little BBs are heavy, right? They're made out of what, I don't even know, copper or maybe. Anyway, they're heavier than water, right? And then the water's motion would push it somewhat, but gravity would be pushing it also. Yeah, then this differential equation wouldn't apply. That's a much harder scenario. Well, it's a different scenario. We'd write down a different differential equation. Yeah. Okay. Alrighty. Okay, so just a reminder, I've already given y'all this speech in some form or another, but vector fields can be thought of in terms of forces. Vector fields can also be thought of in terms of fluids. And a mistake that I've seen students make many, many times in learning multivariable calculus is that so many students will pick one and decide, you know what, I think I understand all this much better in the fluid sense, and I don't really get the deal with forces, so I'm just going to think of all my vector fields in terms of fluids. And that's not going to work. You're going to have to be able to understand. You're going to have intuition for vector fields from both of these points of view to make sense out of all the mathematical ideas we're going to do in chapters 6 and 7. It's really unavoidable. So please don't just pick one. Make sure that you're good with understanding vector fields from a forces point of view and also from a fluids point of view. You got to do both. All right, moving along. So this next section is really weird. Arguably very premature. And so again, let's just talk about pedagogy for just a second. These objects that I'm about to define for you, divergence and curl, are the big tools that we're about to talk about. It takes a lot to get a good intuition and a good understanding of divergence and curl. There's a tremendous amount to say. It's going to take us most of chapters 6 and 7 just to make sense out of what are divergence and curl. Very, very important in engineering, by the way. I know a lot of y'all are engineers. Engineering is kind of, roughly, in some sense, kind of the target audience for this course. Right? And I have had conversations with engineering professors, hey, what's important to y'all, right? What's important to engineering for students to understand about multivariable calculus? And they will not stop talking about how important divergence and curl are for their purposes, right? So it's a really big deal. So, there's different points of view on how to approach teaching these ideas, and one approach is to introduce them once we have the tools necessary to make sense out of them. And that's not what we're going to do here. What this book does is introduce these ideas way early. Again, so that you can have time to kind of digest, time to get a little comfortable with what these things allegedly mean and what they look like physically, so that when we have all the appropriate tools that we can then go through, you'll already have kind of the right way of thinking about them built up in your head, and then as we go through and try to be a little bit more precise and give it context, you won't be sort of doing two jobs at the same time. A, trying to figure out what these things look like, and B, trying to understand why that's how they look, right? So we're going to go with what the book does. I'm going to introduce these ideas way early, before we have the tools to understand them, so that you can have a little time to digest. Okay, so the start of this is gradient. So you all remember this formula for the gradient. I'm going to rewrite that like this, which seems a little weird, but weird though it is, if I were to ask you what this means, wouldn't you naturally assume that, well, we're just going to put the F there and there and there? I mean, that's how you, in some sense, multiply a vector times a scalar, and you'd probably, I think it's natural, you would just write down this as a result. So it's a weird notational choice. Let me further note what's weird is that that's not even really a vector. I'm writing it like a vector, and it kind of isn't, right? What direction is that vector point? Right? It's not really a vector. But this is not our first time to see symbolic nonsense, right? When we wrote down cross product, how did we define cross product? Well, I give you a formula that involved taking a, air quotes, determinant of a, air quotes, matrix, which isn't actually a matrix. Right? Y'all remember that? Yeah, so that was taking quite a liberty with the notation, but very convenient if you do that. And same deal here. Now, this is an example of something that you can define and make precise, but we're not going to do that in this course. I'm just going to introduce this, namely, not the gradient, but just the del operator that applies to a real valued function to define a gradient. I'm going to view this as being an independent thing. And I emphasize you can't call this gradient. It's not gradient. Very importantly, not gradient. Gradient is what you get when you apply it to a function. So please don't call it the gradient operator. Okay, so this is what we call del, and here's one of the several reasons why del is convenient, and that is if you were to try to make sense out of this del dot a vector field. Well, I mean del has coordinates that are like this, and f, such as in that case, has coordinates that look like this. And when you do a dot product says you kind of multiply and add one coordinate at a time. And this is, again, what you would sort of naturally write down. Right? And it turns out that this expression right here is important. This formula is what we call the divergence of a vector field. We will do many powerful things with this expression when we get into chapter 7. Pretty much. And so, yeah, this del operator gives us, well, a very convenient notation for writing it down. So, heads up on this, you will see divergence written, you'll see divergence written in different ways. By the way, another notation, I guess I'll write down here, is some people will call this div f. Which really makes more sense if you think about it. Right? This is an abbreviation of divergence. But in practice, my experience has been I see this much more commonly. So heads up. Okay. All right. Now, where does this come from? Can't tell you. I'll show you later. That's the way it kind of has to be. So what I am going to do, though, is tell you what the punchline is going to be, and we will flesh out a lot more details when we get into Chapter 7. But again, just to give you a little time to sort of chew on it, roughly speaking, what divergence represents is this right here. It's, in some sense, the extent to which the vector field represents a fluid that's kind of evacuating away from, or sort of flowing away from some wherever it is that you were evaluating the divergence. I know I have given you no reason to believe that other than what possible confidence you may have in me and the book. Right? But this is what I claim. This divergence represents the extent to which the fluid is flowing outward away from some vicinity. So an easy example, just to see this in action. This doesn't prove anything, right? But this is at least kind of tracks with the claim that I just made. Here is a vector field. This is what that vector field looks like. Y'all may recognize that from early in the lecture. Right? And if you take this vector field and if you compute del dot, namely if you compute the divergence of this vector field, that divergence evaluated at the origin you see is 3, which is positive. So this positive value 3 this is how divergence communicates to us in this scenario, that the fluid is, as you see right here in the picture, flowing outward away from that point, like so. Is that cool? Again, this doesn't prove anything, but this is what I mean when I say divergence indicates sort of an outward flow, kind of like this. Okay. Now, real quick thought I want to plant, and then we'll call it a day. Let's ask just physically, what does this look like? Right? What's the physical interpretation we would make of this? There's a couple of different physical interpretations. I could imagine that, I was out in my backyard and I bought some little gadget online that emits a super high frequency, and all the mosquitoes that were around me just start going away because they don't like that little high frequency sound. I've always wished to have such a thing anyway, right? So let's imagine that I have such a tool. Well, this could represent the flights of the mosquitoes, right? Which, if that were the case, because the mosquitoes are all running away from me at that point, this represents the process of there being less mosquitoes around me. Namely, this represents a decrease in density, a rate of decrease of density. That'd be one interpretation, right? Now, here's a different interpretation, totally different physical interpretation from the exact same picture. Maybe there's like a light bulb there, and light bulbs shoot out photons, and photons, right, are being generated. It's not like there was a bunch of photons and they're departing from my general vicinity. No, I'm generating photons. I'm not losing photon density. Photon density is, in a steady state situation, photon density is constant, right? The number of photons here in between my hands is constant, pretty much, right? So anyway, just keep in mind, how you interpret divergence physically depends on, which kind of scenario are you in? Doesn't always have the same interpretation physically. It does always have this commonality of the picture will represent an outward flow, kind of like this one. And this makes a good place to draw the line. Picking up here next time, tomorrow. So see y'all later. Have a good one. Don't forget to come talk to me if you came in after I did attendance.
I'm so sorry about this morning.
Let's see here. Let me just get this.